All right, thank you so much for the invitation and the opportunity to talk here. So today I would like to talk about these Patterson-Sullivan measures for Anosov subgroups. So these Patterson-Sullivan measures were introduced by Patterson and Sullivan in 80s to understand the limit set of Kleinian groups. So Patterson started this theory for Fuchsian groups, and then Sullivan generalized them for Kleinian groups. So one application of this theory is that one can understand the growth rate of orbits of Kleinian groups in hyperbolic n space to the limit set to the Hausdorff dimension of the limit set of those Kleinian groups. So our goal is to extend this theory for in the higher rank for this special class of subgroups called Anosov subgroups, which were introduced by Labouri in 2006. So before going to this higher rank theory, so let us review this theory in the rank one case. So for the hyperbolic spaces. So let Hn, and also please stop me anytime if you have any questions. All right. So here's the classical setup. So let Hn be the n-dimensional hyperbolic space. So we think of this hyperbolic space in the unit ball model. So it is like as a space, it can be thought as the unit ball in the Euclidean n space with a Riemannian metric of constant -1 curvature. Okay. So the boundary of this unit ball, which is n-1 dimensional sphere, so that gives a compactification of this ball. It is called it is called the visual boundary of this Hn. So the isometric group of this n-dimensional hyperbolic space is a Lie group. It is so if we are only considering the orientation preserving isometries, then it is PO n, 1. So action of this PO n, 1 on Hn that extends to this boundary sphere by conformal automorphisms of this sphere. So by a Kleinian group, we mean a discrete subgroup of this Lie group PO n, 1. So the limit set. So let's take some Kleinian group gamma. Then if you pick just any point in Hn, then you can look at the orbit of that point in Hn. So since gamma is discrete, that orbit cannot accumulate inside the hyperbolic space. So it has, but since it is like if we take some infinite Kleinian group, so the orbit has to accumulate somewhere. So it accumulates on the boundary of the hyperbolic n space, which is the boundary is Sn-1. The set of all accumulation points is called the limit set. In particular, this limit set is independent of the choice of this origin x. So it's a set in this boundary sphere which is associated with gamma. Okay. So in this talk, like we only assume this finitely generated group. So all the discrete groups we are considering today, they will be finitely generated. All right. So any question about this? All right. So the question that we'd like to address is the following. So let's pick some point x0 in Hn. Then the gamma translate of we pick some Kleinian group gamma. Then we can look at the orbit of gamma. So orbit of x0 under this action of gamma. So the question that we would like to ask that so how fast these orbits grow from this point x0. So here is what we mean by how fast it grows. So we can consider this counting function as nr. So this counting function, this counts the number of orbit points which are, so nr means the number of orbit points which are within distance r from x naught, which is also equal to this intersection, the number of points in this intersection of the ball of radius r about x naught with the orbit of x naught. Okay, so we would like to understand how fast this function nr grows as r goes to infinity. Okay, so let's look at some basic examples. For example, if gamma is a cyclic group, which is generated by this single element gamma, then when gamma is hyperbolic, then it can be shown, it's not too hard to show that this function nr grows almost linearly as r grows. So almost linearly means so this number nr can be bounded above and below by some linear function. Okay, linear function on r. Okay. Now, when gamma is parabolic element, so I didn't define what hyperbolic parabolic means. So hyperbolic elements are those, hyperbolic isometries are those isometries of Hn which has, so any isometry of Hn, like if it has infinite order, then it has to fix some point on the boundary at infinity, which is the boundary being Sn minus 1. So gamma is hyperbolic if it has exactly 2 fixed point. It is parabolic if it has 1 fixed point. So when gamma is parabolic, then one can show by some computation that this number nr grows exponentially with r. Okay. Now, in most interesting examples, like if we exclude these elementary examples, so this type, so the examples in the previous, so in this line, the example of groups are called elementary groups. So elementary groups are which are like virtually abelian. Okay. So if we exclude those elementary examples, like, so if we take like the most interesting class of non-elementary Kleinian groups, then this function nr, this function grows exponentially fast with r. So one example can be thought as the following. So if one takes a co-compact lattice, co-compact lattice gamma in this PO, in this Lie group, like PON1. So co-compact means the quotient of the Hn by gamma is a compact space. So in that case, this number nr, this grows exponentially with r. So the reason is that this number nr can be one can show that this nr grows as fast as the volume of ball of radius r grows in Hn. Okay, and this volume of r balls, this grows exponentially fast, and hence nr also grows exponentially fast. Maybe any question about this? Okay, so with this, we define the critical exponent of gamma to be the exponential growth rate of these orbits. So by delta gamma, we mean the lim sup of this log of this counting function nr divided by r. Now, a priori, it looks like this function, this number delta, this looks like the choice of base point x naught, but it can be shown that it is actually independent of this chosen base point x naught. Like if we replace x naught by any other point in Hn, then this number remains same. So it's an invariant of gamma. Okay. Now, here is the theorem of Patterson and Sullivan. So Patterson proved it for Fuchsian groups. That means isometric groups of discrete isometric groups of H2, the two-dimensional hyperbolic plane. And then Sullivan generalized it for any n-dimensional hyperbolic spaces, any Kleinian group. So let gamma be a non-elementary convex compact Kleinian group. I'll come to what convex compact means in a moment. Then this number that we defined previously, the exponential growth rate of this orbit, this equals to the Hausdorff dimension of the limit set. So here are two numbers. So one number is this critical exponent delta. So this is growth rate of orbits inside Hn. And this Hausdorff dimension is Hausdorff dimension of the limit set. Now recall that the limit set lies in the boundary. Okay, so Hausdorff dimension is computed as some number associated with some subset of the boundary. So here, so on the left hand side we have some number associated to the orbits which lives inside Hn, and on the right hand side we have some number which is associated to some subset on the limit set which lies on the boundary. So magically these two numbers are equal. Okay. Now non-elementary means again, so gamma is not virtually abelian. Okay. And convex compact means, so if we take the convex hull of the limit set, then convex compact means this convex hull modulo the action of gamma. This is compact. Okay. So this theorem is not only true for convex compact groups. So this was generalized later by Sullivan. So if you take the more general class of geometrically finite Kleinian groups, then also like non-elementary geometrically finite.
Sorry, how is the convex hull computed?
Convex hull computed. So convex hull is so you have some
how is it defined? Sorry, yeah.
Yeah. So you have some set in the limits in the boundary of Hn. So you take. So first you can take all the bi-infinite geodesic lines which connect 2 points in this limit set. So you get some subset of Hn, right?
So the hull is taken in the inside. I mean, it's not on the boundary.
It doesn't lie on the boundary, no.
No, so
it's a subset of Hn. Okay. For example, if you take a co-compact lattice, like the quotient is compact, so that is like trivially convex compact. In that case, the limit set would be full Sn-1, the full visual boundary. And the convex hull of the whole visual boundary would be the whole hyperbolic n space. And the quotient is compact in that case.
So in fact, it will be the quotient of, oh, I see. So you adjoin all the limit points and then take the quotient. So you will, for example, get the compact Riemann surface.
In the case of H.
Yes. Yeah. Okay.
Yes.
Okay. Yeah, thanks.
Yeah. But not like for convex compact, it may not be compact. Like for example, you can take a single cyclic group like generated by some hyperbolic element. Then also, so it has exactly 2 fixed points. The convex hull would be the line. So convex hull of the limit set. So limit set is 2 points on the boundary. The convex hull would be the geodesy connecting them, right? And if you take the quotient of that line by this cyclic group, that would just be a circle. Okay. So that is also compact. But the surface has 2 ends, so it is not compact in general. So convex compact is a generalization of these co-compact lattices. Yeah.
Okay, thank you.
All right. So now this theorem about convex compact groups was later generalized to geometrically finite groups, which I'm not going to define. So geometrically finite group is more general class of Kleinian groups than convex compact. For example, they generalize, for example, all the non-uniform lattices in this Lie group, in the isometric group of Hn, they are also geometrically finite. So it's something like the quotient in that case would be like this quotient of convex hull modulo gamma. That is like we want that to be finite volume. Okay. So for geometrically finite groups, Julian also proved that the critical exponent is equal to the Hausdorff dimension of the limit set. Now, this was later generalized to any finitely generated Kleinian group by Bishop and Jones, but in that case, one would have to replace this full limit set by certain part of the limit set containing the conical limit points. So if in this theorem, if you replace this limit set by this conical part of the limit set, then also the critical exponent of the group would be equal to the Hausdorff dimension of the limit of the conical part of the limit set. Okay, which may be strictly smaller than the Hausdorff dimension of the full limit set. Now there were more work related to this. For example, so the Hausdorff dimension is one class of rank 1 symmetric spaces, like the isometric group. So the isometric group of Hn is one class of rank 1 Lie groups. For other class of rank 1 Lie groups, so this theorem was studied by Corlett and Yotze. And then this study was generalized also in the case of higher rank by various people, starting with Albuquerque, then Kant, and then Link. So they considered certain discrete Jariski-Den subgroup of semi-simple Lie groups, and then they studied this this theory. Okay. Now I'd like to make some comments about how this theorem is proved. So this theorem was proved. This theorem was proved using what's called the Patterson-Sullivan measures. So to define these Patterson-Sullivan measures, one first starts with this alternative characterization of this critical exponent. So again, we have some Kleinian group gamma. Okay, so associated to that Kleinian group and some fixed point x0, one can define this Poincare series GS, which is sum of these numbers. Okay, then the critical exponent. So here this S is any real number. Okay, so this critical exponent of gamma is then infimum of all such S, such that this series GS converges. Okay. For example, if you take
this will be a function of x0.
Huh?
So this will be a function.
This is a function of x0. Yes. Yeah. So we are fixing x0, so it's just a number. It's just a sum of numbers.
But in general, this would be a function.
Yes. One can
quotient.
realize GS as a function of x0. And also so the convergence of this series doesn't depend on x0. So if the series converges for one x0, then it would be.
Yeah. So in particular, this will actually define a function on the quotient.
Exactly. Yeah. Yes. Yeah, because this function is also gamma invariant.
Okay.
Yeah. So that defines a function on the quotient. Yes. So the critical exponent delta can be shown to be equal to this infimum of all such S for which this series GS converges. Okay. So using this series GS, one constructs this class of probability measures on Hn union this compactification. Okay. So on this compact space. So for every S greater than this critical exponent, we know that, so by our definition, this characterization, this series GS converges, right? So one can consider these probability measures, which is, so at every orbit point gamma x0, one assigns this amount of Dirac mass, this e to the power negative S times the distance between x0 and gamma x0. So that will define a measure on the orbit of gamma x0. And then since this total mass is, so the total mass of that measure is exactly the denominator. And since S is greater than delta, so the series converges, hence the total mass is finite. So we could normalize that measure to get a probability measure, which we denote by mu x naught comma x. Now, of course, this measure depends on the chosen base point x naught. Okay, so yeah, so for every S greater than delta, we have this well-defined probability measure on this compact space. Okay. Now, when gamma is convex to compact, this series, this pointer series here, so that diverges if you replace this S by this critical exponent of gamma. Okay, this is not very obvious why this should be true, but one can assume this for a fact. Okay, that at this infimum point, this series actually diverges. I mean, it may converge or diverge. We are not sure, but in the case of convex to compact, this actually diverges. So when you move this number S closer and closer to this critical exponent, we can see that this denominator actually gets larger and larger and diverges to infinity, right? So every point mass here, like at every orbit point, we have this point mass, right? So if you divide that point mass by this number, which gets larger and larger when S goes to S gets closer and closer to the critical exponent, then when delta, like if you take the weak limit of this, so if you take the weak limit of this probability measure as S goes to this critical exponent, you get some. So since we are in this compact space, so that has to subconverge, like after passing some subsequence, that has to converge to some probability measure, and that probability measure, like any orbit point, would have mass 0 for that limit measure. Okay, so but we still have a probability measure, so it has to be supported somewhere, and one can show that the support of that limit probability measure actually lies inside the limit set. Okay. Now, any such limit of these probability measures, they are called Patterson-Sullivan measures. So the support of Patterson-Sullivan measures, they are contained in this limit set. Okay, so the whole HN is actually null set, because at S this denominator is just infinity. So every point, every orbit point has 0 mass, right? When
Shubhadeep, so the thing, there is one thing. So there, you said that there are possibly different weak limits, right? There's a relationship between them.
I couldn't hear it. Could you repeat that?
I'm saying that you said that there are possibly different weak limits, right? And so the Patterson-Sullivan measure is not a single measure, but different, possibly a family of measures.
Exactly.
Can you say something about a relationship between the different limits?
So in the case of convex compact group, actually one get a unique weak limit. So this is one of the application of this theory, but in general, I think one may get different weak limit if you like pass to different subsequences which converts to delta.
Is there any relationship between them?
Relationship
between two different, yeah.
Relationship.
So are they? So for example, are they in the same measure class?
If you like change the base point?
No, I mean, you're saying that you are looking at, see, what is it? You're looking at uniform measures on orbits and uniform probability measures on orbits, and then passing to weak limits. You might get two different subsequential limits, and you are going to get two different probability measures supported on the limit set. Any two such subsequential limits, are they in the same probability, in the same measure class, which means that whether the Radon-Nikodym derivatives are uniformly bounded, are L infinity,
yes,
both in the forward and backward directions. Yeah.
So so again, if you take convex compact, the weak limit has to be unique. So let's exclude that case. If you, I'm not sure actually what happens in the other class of Kleinian groups, whether they would be like in the same measure class. Like if you take two different,
Okay.
maybe
Okay. Thanks.
I'll
Yeah.
get back to you about this. Yeah, but when we are in this convex compact class, this weak limit has to be unique. I mean, doesn't matter which like sequence you choose converging to this delta, this limit has to be the same. Like, doesn't depend on the subsequences. Okay. Yeah, but it may be like I'm not sure what happens in the other like for groups which are not convex compact. Yeah, maybe we'll come back to it later.
Sure.
All right. So for every point x, then we have this like some limit measure mu x naught. Now, for if you vary this x, you get different limit measures. This mu, which, and we can consider the class of all such limit measures mu x. Okay. Now, so this class of limit measures, these are called Patterson-Sullivan density, and they satisfy these two relations. Okay. So they satisfy these two relations that so if you take any Borel set B in Sn, then this mu x of gamma inverse B equals to mu of gamma xb for every Borel set. And then the Radon-Nikodym derivatives. So if you pick 2 points, x and y, then this Radon-Nikodym derivative is given by this expression. At any point, xi is given by this expression. E to the power negative delta is the critical exponent. And then times the Bushman function, some normalized Bushman function at xi. So b xi x minus b xi y. So this difference can be thought as the distance between two horospheres centered at this point xi, which are passing through x and y. Okay. So any measure, any density which satisfy these two relations, they are called this gamma invariant delta conformal density. Okay. So gamma invariance means this condition is satisfied, and conformal means this second condition is satisfied, that the Radon-Nikodym derivatives are in this form. Okay, maybe any other question? All right. So here's the theorem of Sullivan about this Patterson-Sullivan density. So again, let gamma be any convex compact non-elementary Kleinian group. Then this limit measure mu is a unique delta conformal density. Okay. So this is equivalent to this following, that the action of gamma on the limit set is ergodic with respect to any of these measures mu x. Moreover, the delta dimensional Hausdorff density on the limit set is also a conformal density.
So where is dependence on x go? Suddenly you're talking about a unique mu. Is that?
Yeah, so the class of all such probability measures.
So when you say unique, you mean unique up in the
unique means unique as a density. Yeah. Yeah, so any density, like any other density which satisfy these two relation, they will also be like up to some like rescaling, they would also be.
Is that what a density means? A Radon-Nikodym class? I mean,
yeah. So by density we can like by this term gamma invariant delta conformal density, we can say that it's a class of measures
Okay.
like varying with the base point x, class of measures on the limit set, or maybe the visual boundary, which satisfy these two relations. So any other, so the theorem says that any other such density would be same as the Patterson-Sullivan density up to some linear scaling. All right. So the second part of the theorem is that that the delta dimensional Hausdorff density on the limit set is also a conformal density, and it has to be equal to the Patterson-Sullivan density. So any delta dimensional Hausdorff measure in particular is finite and positive. So therefore, the Hausdorff density of the limit set is this critical exponent delta. Okay. All right. So next we are going to talk about, so our goal is to generalize these theorems in higher rank in the class of Anosov subgroups. So Anosov subgroups are certain discrete subgroup of semi-simple Lie group of non-compact type. In this, like, let us first define them precisely for this semi-simple Lie groups SL and R. Okay, so we are going to define this this Anosov subgroups for SL and R only. Okay, so for any matrix in SL and R, we have these singular values of this matrix. Okay, and we order these singular values as in this decreasing order, sigma 1 less than or equal to sigma 2 and up to sigma n. So we have n singular values. Okay. Now, so here is a definition of Anosov subgroups. So originally Anosov subgroups was defined in terms of dynamics. So that was the original viewpoint of Labouri. But after Labouri's work, so there are now many equivalent characterization of Anosov subgroups in terms of different things. So here is one of them in this specific class of, in this case of SL and R. So suppose gamma is a finitely generated group. Okay, then given some generating set S, we have this word length distance function on gamma. Okay, so a representation rho from gamma to SL and R is called PK Anosov, where K is like any of these numbers, 1 up to n minus 1. If one can find these constants L and A such that this holds, log of this kth singular value divided by the k plus 1 singular value. So this is greater than or equal to L inverse the word length of gamma minus A. Okay.
What is PK? What is P sub K?
Yeah, so we are like just denoting this quantity by D sub K. So this depends on two things, K and gamma.
No, that's right. So, but capital P sub K is supposed to denote some parabolic subgroup or something like that, right?
Yeah. We'll come to that.
Okay, thank you.
Yeah. All right. So when n equals to 2, that means SL2R. So SL2R is the isometric group of H2. Then we can define a distance function on this symmetric space, like on this symmetric space G mod K, for like this maximal compact SO2R. Okay, and this distance function can be given by like D of distance between 2 points G1. So I should have put this G1 times SO2R, G2 times SO2R. So distance between 2 points in H2 by this number D1 G1 inverse times G2, where D1 is our, so we replace this K by 1. So D1 is like log of sigma 1 divided by sigma 2. And one can see that this distance function is, first of all, G invariant, this SL2R invariant, and it is actually the distance function given on H2 by this constant negatively curvature metric on H2. So constant negatively curvature metric of, I think maybe, yeah, it may not be, the curvature may not be negative one, but it's still constant. Okay. So in that case, this equation, this inequality, dk greater than or equal to L inverse the word length of gamma minus A. So this just means that this orbit map is a quasi-isometric embedding. Okay. And this is actually equivalent to being convex compact. So in general, in the rank one, like this Anosov property in the for the rank one Lie groups just mean convex compact. So Anosov subgroups are higher rank generalization of convex compact Kleinian groups. But when n is greater than or equal to 3, that means we are in higher rank. This Anosov condition is actually strengthening of just quasi-isometric embedding to the symmetric space. So this condition in particular is strengthening of this quasi-isometric embedding. Okay. Now, one example. So all convex compact Kleinian groups are rank 1 Anosov subgroups. In higher rank, examples of Anosov subgroups are given by these so-called Hitchin representations. So Laburi proved that these Hitchin representations are Anosov. So Hitchin representations are, first you take some Fuchsian representation of surface group into SL2R, and then you embed SL2R in SLNR by some irreducible representation. And then you take the composition of these two. So the composition is called Fuchsian representation of this fundamental group in SLNR. So if you deform these Fuchsian representations in SLNR, then you get different representations. And Laburi showed that all these representations are actually PK Anosov for every K. Okay. And these also correspond to like what's called the higher rank Teichmuller space, the representations of surface groups in SLNR. Okay. So Anosov subgroups can be defined for any other higher rank Lie groups of non-compact type. So let G be a semi-simple Lie group of non-compact type and K be a maximal compact subgroup. So we need some mild conditions on G. For example, we want the center of G to be finite and like so on. And let X be the symmetric space of G and P be some parabolic subgroup, which we may restrict to the case that the parabolic subgroup is actually conjugate to its opposite. Now, given this choice of parabolic subgroup, there is a class of P-Anosov subgroup. So I'm not going to define this P-Anosov subgroup in detail. So one of the definition is given by this this statement, which was shown to be equivalent to Laburi's definition by Kapovic, Lieb, and Porte. So suppose gamma is a P-Anosov. So a discrete subgroup of G is called P-Anosov if, like, a finitely generated discrete subgroup is called P-Anosov if the orbit maps from gamma to gamma x naught is a quasi-isometric embedding. So on the left-hand side, we have the word metric, and on the right-hand side, we have the distance function induced by the Riemannian metric of x. Okay, so with respect to that, those distance functions, and these orbit maps are quasi-isometric embedding, and gamma is uniformly regular. Okay, so I'm not going to define what this uniformly regular means, but in the previous slide, this whole thing means it is quasi-symmetrically embedded and uniformly regular. Okay. All right. Now, given such gamma, there is a unique continuous. So whenever we have we have, so whenever gamma is an anosov subgroup, it is necessarily true that gamma has to be a word hyperbolic group. Okay, so in the original definition of Labourie, he took some word hyperbolic group and then he defined anosov representations. But in this definition, we actually don't need to start with some word hyperbolic group. It's actually a consequence of these two properties that gamma has to be word hyperbolic. Now, given such anosov subgroup gamma, there is a unique continuous gamma equivariant dynamic preserving transverse map from the boundary of gamma to this partial flag manifolds G mod P, where P is this parabolic subgroup. Okay. Now, so dynamic preserving means, so attracting point goes to attracting points, and transverse means, so we are going to define what transverse means in the case of SLN R. Okay. Now, this image of this unique map is called the limit set of gamma. Okay. Now, when G is SLN R, then this PK anosov, the parabolic subgroup corresponding to this PK anosov is actually the parabolic subgroup corresponding to this partial flag manifold. So containing partial flags, this VK subset of V. So some K dimensional subspace of Rn, subset some n minus K dimensional subspace of Rn. So the fixed point of this, so there is a SLN R action on this flag manifold, and the point stabilizers are the parabolic subgroups which correspond to these PK anosov subgroups. Okay.
What do you mean by continuous from delta gamma?
So delta gamma is a topological space, and this I didn't understand.
Delta gamma is
So delta gamma is the boundary of the group. So there is a.
Okay.
Oh, maybe I didn't say it in. Yeah. So the delta gamma means the boundary of the group.
Okay. Mm-hmm.
Yeah, the Gromov boundary of gamma.
Okay. Mm-hmm.
Yeah. So it's a.
Just to fix an example, what should I take? Co-compact lattice in SLNR?
One can, for example, take this Fuchsian, like this Hitchin representation. So in this case, the boundary is just a circle.
Right.
Yeah, and then, so this is a map from the circle to this partial flag manifolds, which is embedding.
Okay, so I kind of just having a hard time processing the definition. So in terms of just thinking in terms of lattices, can I just take a standard non-uniform? Can I just take SLNZ? Is that going to be a PK anosov?
No.
SLNZ, no. Actually, lattices in G,
except for n equal to 2.
Huh?
Right, yeah. Never mind, go ahead, yeah.
Yeah, in higher rank, actually, lattices are never anosov.
I see.
In like, you can look at this. So when you take, like, you can find elements which have like you can find a sequence element in G which diverges to infinity, but this ratio can be like this log of
I see.
as small as you want.
Oh, I see. So this is not. So these are not lattices co-compact or otherwise. They're not lattices.
No, in higher rank, yeah. That's why like lattices are never anosov in higher rank.
I see. So I see. So the thing that you're going to construct is, because this Benoit, Kant, and Abercrombie, sorry, they have Patterson-Sullivan theory for lattices in SLN. For instance, right?
Yes.
And so you're trying to move beyond. So your construction is kind of not in that spirit.
They considered more general class than lattices. I mean, lattices are actually
discrete Zariski dense circles. Right?
So, as far as I remember, they also needed some regularity condition, which probably I'm not sure actually now.
I see.
Maybe, yeah, maybe lattices don't satisfy those conditions. Yeah. Yeah,
I
I'm
see.
not sure.
All right. Can you tell us a little bit more about how this, how Labori was motivated to get into this kind of? It seems, I mean, coming from a dynamical perspective, this seems kind of a little bit contrived. The definition.
Yeah, maybe. So since I just have 15 minutes.
Okay, okay, all right. We can discuss later.
Yeah. Yeah, maybe we can talk it later. All right. Okay, so the image of this this embedding is called the limit set. Okay. So yeah, so in the case of SLNR, this and the class of P-NSF subgroups, one can like the parabolic subgroup would correspond to these flag manifolds. Now this transversality condition that we have here is that means that for every two distinct points x and y on the boundary of the group, the k-plane is transversal. The k-plane corresponding to x is transversal to the n minus k plane corresponding to y. Okay, so vkx would plus vkn minus ky, that would span Rn. Okay, so these two complementary dimensional subspaces are transversal. Okay. Now, so we would like to define this Finsler metric on the symmetric space. So let P be a, again, so we fix some parabolic subgroup P, and gamma is some P-NSF subgroup. On the symmetric space X of G, we consider certain Finsler metric. Finsler means so some metric which are defined by putting some norms on the tangent spaces of X at every point. So we consider some Finsler metric which behave nicely with the P-NSF class. So I'm not going to detail the definition of these metrics for the general symmetric space and the P-NSF class, but for this class of P1-NSF subgroups in SLNR, one can take this metric to be by this function. So distance between 2 points G1 and G2 in the symmetric space X can be given by this formula, this log of the first singular value of G1 inverse G2 divided by the nth singular value of G1 inverse and G2. Okay. Now, so the reason of choosing Finsler metric is that with respect to this metric, the asymptotic nature of this NSF subgroups is well understood. So one consequence of this like one nice thing about choosing this matrix is that if you take gamma orbits in X with respect to this metric, then the orbits should become delta hyperbolic metric spaces. Okay. Now, this I'm not sure whether this holds if you replace this df by the Riemannian metric of X, whether the orbit should become delta hyperbolic metric spaces, because we are dealing with non-positively carved spaces X. Okay. Now, so given this Finsler matrix DF, we can similarly define this critical exponent, which is the.
Just say one sentence why you're forced to go outside Riemannian matrix to Finsler matrix.
So
yeah.
So for Riemannian metric, like if you just take like so for Riemannian metric, we just know that these orbit maps are quasi-isometric embedding, right? So since this X is non-positively carved, the image of this quasi-isometric embedding may not be a delta hyperbolic space. So one easy example is like one can embed this real line into R2 by this V, and the image is not delta hyperbolic because triangles are not thin. So, but with respect to this Finsler metric, we actually have the fact that these orbits are delta hyperbolic. Actually,
Exactly what you mean by, I mean, delta hyperbolicity for the real line embedded in R2 with the mod X function. I mean, if you look at the intrinsic metric, then that is still, I mean, it's still delta hyperbolic, right? I mean, it's, see,
no,
basically, if you look at,
you,
so the induced metric between 2 points is going to be some 1 by C sum. And the thing is, how are you going to compute delta hyperbolicity? You're going to take 3 points on the real line. No? And so triangles are going to be just like triangles in a tree, equipped with some metric. So
yeah, so
I
this
mean,
V is the quasi-isometric embedding, right?
yeah, so it's a quasi-isometric embedding, which means that if you look at the Riemannian distance between 2 points, that is comparable to the metric in the hyperbolic space, in the space that you mapped in originally, right? And so, what exactly is the problem with that? I mean, it's not a geodesic metric space. Is that your problem?
Yeah. So what I
mean,
know,
2 points which are say at distance square root 2. If you go in the space, you will spend more time to reach there. If you
yeah. So
spend say, time
like this may not be the right logic, but in this V, one can, if you pick 3 points, for example, the corner in the V and then 2 other points which are very far, then the triangle would be thick, right? Like although the edge connecting.
No. That I understand that what you are saying is that R2 is not Gromov hyperbolic, but but that does not mean that the space with the induced metric is not Gromov hyperbolic.
I think it is not Gromov hyperbolic. So there is a notion of Gromov hyperbolic. So first of all, it's not a geodesic space. So therefore, this.
That's correct. It's not a geodesic metric space. So the problem is not with hyperbolicity. I think the problem is with it's not being a geodesic metric space, right?
Yeah, but there is still a notion of hyperbolicity in terms of like this
4-point condition, right?
Yeah.
So if you take the 4-point condition, then it is satisfied. No?
Then it is not hyperbolic, right? Or is it?
No, the 4-point condition is satisfied for. I mean, you can take the real line and you put any odd metric on it, really, and it's so long as it is proper. No? See, what will be the shortest path between 2 points? You have to go through that V essentially, even if you look at it coarsely. You have to coarsely go through that. Yeah.
So that works for geodesic spaces. For the 4-point condition, we don't need to have paths, right?
That's correct, but you can still take something like a sequence of points which are separated by say distance 1. Any 2 pairs are separated distance 1, and the sequence of points is such that minimum distance of separation of the sequence is 1, and maximum distance of separation is say 4. And then you do have a sequence of points, and you can have a coarse geodesic.
Yeah, it's probably a computation. I may be wrong. Yeah, it's probably just a computation. I think we can.
Oh, I see what you're trying to say. Okay, fine, fair enough.
Yeah.
Okay.
So what holds true is that if you take some hyperbolic space, a function from a hyperbolic space into another hyperbolic space, which is a quasi-isometric embedding, then the image would be hyperbolic as well. But like if you allow non-positively curved on the right-hand side, then the image may not be. So we define this critical exponent of gamma with respect to these metrics, okay, which is again this infimum of S, such that this series converges, okay. Now, so now we define the Patterson-Sullivan measures. So when G is SL2R, then the visual boundary can be identified with G mod P, where P is the parabolic subgroup of SL2R. Okay. So in the higher rank case, these partial flag manifolds G mod P, they can be thought as some partial compactification of the symmetric spaces. Okay. And so the limit set lies in this partial. So we have the symmetric space X and some partially attached boundary, which you can intuitively think of this G mod P. And then we have the limit set which lies in G mod P. Okay. Now, with this, we can think of this limit set to give compactification of the orbits of gamma. Okay. And so if you attach this limit set, then this orbits, this gamma x naught union this limit set would be a compact space. And on this compact space, we consider these probability measures, which are again constructed in the same way. So we take these probability measures on this gamma x naught, okay, for s greater than delta, and then we let s converge to delta and take the limit of these measures. Okay, so that will again not be so the whole gamma x naught would be null set for that measure. So it will be supported on some subset of the limit set. Okay, so any such limit, any such weak limit is called again a Patterson-Sullivan measures. And again, we can vary the base point x naught to get this class of measures, which we call the Patterson-Sullivan density. Okay. So this Patterson-Sullivan density satisfy these two conditions, like similar to the conformal and the equivariant and the invariance condition that we had in the rank one in the case of hyperbolic spaces. So mu satisfies this gamma invariance property that for every Borel set, the measure mu x, so with respect to x of gamma inverse B equals to mu gamma x of B, okay? And the Radon-Nikodym derivatives, so d mu x, d mu y, at some point xi on the limit set is given by this formula, e to the power negative the critical exponent times. So these are certain generalization of the Bushman functions in the higher rank, okay? So this can again be thought as horospherical distances between two horospheres. Okay. Now, so here is the theorem. So let gamma be some non-elementary Pianosov subgroup. Then this critical exponent delta is positive and finite. The density mu is non-atomic, and the support is exactly support of mu is exactly the limit set. Moreover, this action of gamma on this limit set is mu ergodic for every probability measure mu x in mu. So consequently, this mu is the unique gamma invariant conformal density supported on the limit set. Okay.
And this delta gamma need not be equal to the critical exponent of the hyperbolic group that you started off with. That's right. Is that correct?
Critical exponent of the hyperbolic group with respect to the word metric, is it?
That's
So
right,
the thing is that if you change the word metric, for example,
no, you. That's right. That's right. So the thing is,
change.
certainly there is. That's correct. So I mean, see, there is this. There is some theory of if you allow your word metrics to vary, and then you can take an infimum. Or supremum, I forget which one.
So
there is
some. So the metric is given. So we had this metric defined on X, the whole symmetric.
I understand. What I'm saying is that these. So the conformal density that you get just from the group itself need not be equal to this delta gamma which you are getting in terms of the embedding, right? So I mean, very simple rank one situation. If you have a totally geodesic hyperbolic, say a surface group that has delta, I mean, intrinsically the limit set Hausdorff dimension is 1, but you embed it into a hyperbolic free space. If it's totally geodesic, the delta is still 1. But if you quasi-conformally deform it, you can make it as large as possible, up to 2. Right? So what I mean, so here also the similar phenomenon happens where delta gamma can be made different. Is that correct?
So of course, if you like perturb the representation, then this delta gamma varies. So in certain cases, it is known that this delta gamma actually varies analytically with respect to the representation. And so in the higher rank, actually, I wanted to say about this in the very last slide, but I don't know how much time I have. So in the higher rank case, so as in the case of rank 1, like if you take a Fuchsian group in Fuchsian, like in the isometric group of H3, then if you perturb it, then the critical exponent actually increases from 1. In the higher rank, like in certain cases, it is observed that the critical exponent actually decreases from the critical exponent of the Fuchsian representation.
Oh, it's possible. I mean, so you can have Anosov representations where if you look at say take the Fuchsian representation into SL2R, map it into SLNR by the irreducible, and then perturb that representation to get all Hitchin representation. Is it possible that the critical exponent goes down?
Yes, it actually goes down. So it is exactly 1 when it is Fuchsian. If it is not Fuchsian, then it is strictly less than 1. So this was shown by
strictly greater than 1.
No, less than 1 in
less than 1.
Yes.
So that's exactly opposite of what happens in the rank 1 case, right? In the rank 1 case, it's I see.
Yeah, so it's a very interesting phenomenon in higher rank which is in contrast with the rank 1 case, that the critical exponent actually drops from the Fuchsian representation.
Very interesting. Very interesting. Okay, thank you.
Yeah, actually, I wanted to put this in the last slide. So let me briefly describe the Hausdorff dimension. So on this partial flag manifold G mod P, one can define a distance using some Gromov product. I'm not describing what all this means, but in the specific case of this partial flag manifold associated to this P1 Anosov representations, so the partial flag manifold is the set of all partial flags lying contained in hyperplanes in Rn. So in that case, this distance can be given by this formula. So distance between two partial flags, L1, H1. So L1 is a line contained in the hyperplane H1, and L2, H2 is sine of this angle between L1 and H2, square root of that, and times sine of this. So one can see that it's not actually a genuine distance function, because one can pick two distinct points and can get this distance to be 0. For instance, if L1 is a subspace of H2, then this is just 0, right? So this is not a distance function, but it's still a well-defined non-negative function on G mod P pair of points. Now, when you here is our theorem in regards to these functions, that there is some small epsilon naught greater than 0, such that given any epsilon less than or equal to epsilon naught, if you take the epsilon power of this distance function and then restrict to the limit set, so that function will be by Lipschitz equivalent to some actual distance function on the limit set. Okay, hence one can talk about the Hausdorff measure of that distance function, which is by Lipschitz equivalent to this function. Okay, and that Hausdorff measure is actually a partition-Sullivan measure. It is a conformal measure, and from that one can derive that the Hausdorff dimension of the limit set is this critical exponent divided by epsilon. Now one can take this, for simplicity, one can just assume that this epsilon is 1. And in that case, the Hausdorff dimension is exactly like with respect to this metric is this critical exponent. Okay. Maybe any question? All right. So in the case of echelon R and P1 anosov class, so one can, so we have done all these things in like outside Riemannian metric. So Riemannian metric of the symmetric space and the Riemannian metric of the flag manifolds. Now one may ask this question that what happens if you take, in place of this Finsler critical exponent, if you take the Riemannian critical exponent and the Hausdorff dimension computed with respect to the Riemannian metric on the flag manifold. So when you take a P1 anosov class, when you take a P1 anosov group, gamma, one can show that the Riemannian metric of this, so the Hausdorff dimension of the Riemannian metric, Hausdorff dimension of the limit set with respect to the Riemannian metric on the flag manifold actually is bounded by two numbers, this critical exponent, which we call like delta 1 comma n, and some other, okay, delta 1 comma 2. So this delta 1 comma n is exactly the critical exponent of the Finsler metric that we defined here. Maybe, yeah. So delta 1 comma n is exactly this the critical exponent with respect to this Finsler metric, okay. And delta 1 comma 2 is some other norm, like critical exponent with respect to some other norm on X. So the Hausdorff dimension of this limit set is between these two numbers. Okay. Now one can show that there are actually representations for which this side is achieved, and there are some other representations for which this side is achieved. So this is best bound. Okay. So now we have in this theorem we have bounded this this Hausdorff dimension of the limit set with respect to the Riemannian metric with respect to, so in terms of two Finsler critical exponent. So one may ask, like, so is it true whether the Hausdorff dimension is equal to the critical exponent with respect to the Riemannian metric on X? So Porti and Sambarino, they showed that if you take some Hitchin representation in SLN R and some suitable normalization of the Riemannian metric of the symmetric space, then this critical exponent of gamma is always less than or equal to the Hausdorff dimension of the limit set. And for the case of Hitchin representation, this limit set is actually a C1 curve. Hence, the Hausdorff dimension is 1. So this critical exponent is always less than or equal to 1. And this equality holds exactly when gamma is a Fuchsian group. Okay. And as we were discussing, this is in contrast with the case in the rank 1 symmetric space, where if you perturb the Fuchsian representation, you get the critical exponent to be higher than 1. So one can ask this naive question, like whether so here we can see that the critical exponent with respect to the Riemannian metric is less than or equal to the Hausdorff dimension of the limit set with respect to the Riemannian metric, right? And the strict inequality may hold for certain representations. So one can ask this question, like whether this theorem holds in general. So if you take a P anosov class of groups, okay, then can you find some suitable normalization of the Riemannian metric of X for which the Riemannian critical exponent is bounded above by the Hausdorff dimension of the limit set? So yeah, I don't know whether this is true in general. This is all I wanted to say. If you have questions.
Thank you very much. So let's thank the speaker. All right, are there any questions?
Yeah, I have disturbed the talk enough, but I still have a question.
Yes,
is it
course.
okay to ask? Okay, so Shubhadeep, what is the I mean, can you just give some kind of a hand-wavy explanation as to why this Hausdorff dimension of the limit set goes down under perturbation, say even in the Hitchin component? I mean, see, the thing is, it's very different from the quasi-Fuchsian case. I mean, this is basically what you're saying is there is a kind of Bowen's theorem, except that the inequality goes exactly
Yeah,
the
and
opposite
that
way.
is tested only for
That's
special
that
type of
instead of-
representation. I mean, for like general Anosov representation, many of the so
No, say Hitchin.
yeah,
Just say Hitchin.
so in the
Let's
higher
keep
rank
it
case, there is a issue of like suitably normalizing the Riemannian metric of this symmetric space, because like if you take a different normalization of the Riemannian metric, then you get different critical exponent. But the Hausdorff dimension is all well defined for any Riemannian metric, right? So there is an issue of correctly normalizing the Riemannian metric of the symmetric space. But if you have done that, like in this case, we normalize this Riemannian metric in a way such that the this embedding of SL2R in SLNR, so the hyperbolic space that has constant curvature -1, like we normalize in this way. Okay, so then this holds true. So the exact reason is is a little bit like subtle, but one can actually show that for Hitchin representations, so this side of the inequality is achieved. Okay.
Yeah, no, I'm asking why.
So
Why does I mean, what exactly contributes to so essentially what you're saying is that related to, say, for example, how fast geodesics diverge? I mean, that's supposed to be the Sullivan inequality, right? So the rate at which geodesics diverge in hyperbolic space is I mean, if you look at, say, basically take two geodesics going out at angle, starting off at angle theta, then the distance between them is going to grow like e power some lambda n, where the lambda is the critical exponent. So that falls below 1, something like that happens.
I don't know, like how, like then you change, like, so if you part of the representation, then we don't have this embedding of H2 anymore, like some equivalent embedding may not.
Yeah, but you can still look at, say, n balls around your origin.
Mm-hmm. So the reason I know it is true is that like the most straightforward reason it is true is that these two numbers are equal for Hitchin representations. So it was shown by, for example, Winhard. So these people. Okay, and this corresponds to some Riemannian. So therefore this critical exponent delta 1 2 is 1. Okay, for Hitchin representation. Now this Finsler metric was actually derived from the Riemannian metric. So if you have some Riemannian metric and you take some so on the positive Weyl chamber we pick some positive linear functional, and then we take the norm with respect to the positive linear functional. Hence, so the Finsler metric is defined from the Riemannian metric. So in particular, the Finsler metric is also less than or equal to the Finsler distance between 2 points is also less than or equal to the Riemannian distance between.
Riemannian. Oh, very good.
Yeah,
I see.
So if you basically change the direction for which this, so if you change the direction, then the Riemannian metric is kind of like, one can say, this infimum of all Finsler.
Yeah.
So therefore,
yeah.
have something smaller. So
very nice.
So the growth rate actually
very
depends
nice.
on the direction we are picking, and it is maximal. So there is a maximal direction at which the growth rate is maximal, and that maximal growth rate is 1.
I see.
And
Very
the
nice.
growth rate is less than that, like in general.
Very nicely. Okay.
Yeah.
All right, great. So thanks again, Suri. This was excellent. And I'd just like to say that Sudeep has kindly agreed to give us another talk with more details on the 22nd. So I'll send an email about that.
Okay. Yeah.
Thanks, Shubhadeep. Very nice talk.
Yes, excellent. Thanks very much. Bye.
See you.